As I said in the first video, you all have been deriving kinematic equations for systems with holonomic kinematic constraints since the beginning of this course. You've been doing this in sample problems, in homework assignments, and even quizzes. So I thought I would just take a second and just show you how you've been implicitly incorporating these constraints into your kinematic equations. These first few examples are actually going to be quite trivial, but they're still informative and useful nevertheless. So let's consider the following systems. Imagine we have a rigid body that can move, that can slide along a horizontal shaft. Again, that's the same as if you had a rigid body that could slide along a horizontal surface. Or let's say we have a, actually let's do this one where we have a channel and we have a point. So a particle that can move up and down in that channel. So let me just draw my reference frames here. First I'm drawing my points of interest, so P, P, and P there. I'll put my reference frame for this system here. One here, and then one here. Okay, so if I were to ask you just to write the position vectors of each of these systems, it would be pretty straightforward, right? You would say that this distance here is x, this distance here is also x, and this is y, and therefore you would write ROP is equal to XA1 for both of these systems. And here you have ROP is equal to YA2. And in each of these equations, you have one coordinate. Right? So in these two equations, that coordinate is x. And in this equation here, it's y. But there's one coordinate. And that's because all of these systems have 1 degree of freedom. And so that's just probably very intuitive to you at this point. But what you're actually doing when you're writing, say, this equation here, you could, I guess maybe this is the long way, but you could write this ROP is equal to x of A1 plus y of A2, and then you add your constraint equation, which is that y, in this case, is equal to 0, which then leads you to the position vector that you originally wrote, XA1. And right, you could repeat that for the following two systems. Now you might say, well, okay, yeah, duh, that was just a really long way of doing this. Well, that's because these examples are, again, we've practiced them, they're just intuitive. As you'll see in some of the sample problems in this week, that writing out your constraint equation may not necessarily be that simple. And once that constraint equation gets complicated, it's not as intuitive to incorporate it. Let's go back yet again to our rotating rod example. Okay. So I mentioned that the holonomic constraint equation for this pivot point here is x squared plus y squared where this is x, this is y. We say that it's equal to L squared. So L is this distance here. And then to write it in our proper form, we have x squared plus y squared minus L squared, right? So this is our constraint. How are we actually incorporating that when we're writing our position vector? It turns out that we satisfy this constraint when we set x equal to cosine theta and y equal to sine theta, again with this being theta. Okay, so you can plug these terms into that constraint equations and you'll get cosine, this is L. You'll get L squared cosine squared theta plus L squared sine squared theta minus L squared equals 0. And you should remember the identity, that is cosine theta squared plus sine squared theta is equal to 1. So we can write this here, and we can pop out the L squared onto the other side of the equation. Again, that just goes to 1, and now we've satisfied that constraint, L squared equals L squared. Okay, so just by writing this position vector, ROP, as L cosine A1 plus L sine of A2, we're incorporating this constraint here. Now you could do something fun. For instance, if you wanted to, let's say we have ROP, we define x A1, and now we have y A2. We can still incorporate this constraint here without actually using theta. So we just say we need a value, or we need an expression of y in terms of x, right, in order to get rid of this variable. So you could take this constraint equation, our x squared plus y squared minus L squared, you can equals 0. You can then write this as y squared equals L squared minus x squared, and that y is equal to the square root of L squared minus x squared. And you can take this equation, if you wanted, and you can pop that in here. And you can write ROP is equal to x A1 plus the square root of L squared minus x squared A2. Just gonna erase that and put this here. This is also a valid expression, right? What's important is it's incorporating the constraint. Here again, you only have one coordinate, x, just like in this way of expressing it, you have one coordinate, theta, right? So this is also 1 degree of freedom. You just now have a different coordinate. Now, of course, when you're going through these, you can imagine from an algebraic standpoint, of course, when we write it in this form here, or consider this form, we can do some clever things like add another reference frame, and then our algebra becomes easier, and then taking derivatives and such becomes much easier. So there's advantages, and there's reasons why this is the common expression and not this. But what's important to know is that you can write x in terms of y, you can write y in terms of x, or you can use this intermediary variable theta to describe that relationship between them. But you only have one variable, right? Because again, system is 1 degree of freedom. I do want to emphasize that the point of this video is not to show you or teach you a new way of incorporating constraints. It's right. So I don't want you to think, oh, now I have to write my position vectors like this, or now I always have to write out a full or more expansive equation and apply these constraint equations. For these cases that you've been working on, that you've been doing, do keep intuitively incorporating those constraints. The point of this video is to show you how you've been incorporating them so that when we, in the next video, introduce a constraint equation that might be a little less intuitive or might be more complex, that you know what the general process is.